Okay, picture this. You're standing in a forest. It's raining. You see water dripping down trees, soaking into the ground, forming little streams.
Hmm.
It's, this whole complex system, water moving everywhere, always changing. But how do we actually measure it? Like, how do we quantify the total amount of water moving through a specific area, a watershed, over time?
Right, and that's the big question, understanding that cumulative water runoff. Well, that's where some math concepts, maybe ones that seem a bit abstract at first, become really, really useful.
Calculus, right? Our
Yeah,
sources dig into that connection.
exactly. Differentiation and integration specifically, they're critical tools for understanding the actual hydrological processes driving that runoff.
Okay, so let's unpack that.
Yep.
We're looking at how these mathematical tools, things you might be wrestling with in class, actually help describe something very real, like water flowing through a forest.
Precisely. And if you're maybe a student in, say, forest resources technology or something similar, and you're wondering, where does this calculus stuff actually apply? Then this deep dive is definitely for you. We're really exploring how differentiation and integration aren't just equations on a whiteboard. They're essential for looking at, real environmental systems, like watersheds.
So the core idea from the sources
Huh.
is it's about those hydrological processes,
Yeah.
things like rainfall intensity, how fast water sinks into the soil, channel flow speed. They set the rate of water movement.
That's it. And understanding that rate, that instantaneous change, how much water is moving right now or how quickly the soil is getting wetter, that's where differentiation is key. It helps us pin down and measure those specific rates, which, are always fluctuating because the watershed itself is so dynamic.
Right. So differentiation gives us that snapshot, the rate at one specific moment or maybe one specific place. But how do we get from that to the total? The total water over an hour or a day or through a whole storm?
And that's where integration comes in. It provides the necessary formulation if differentiation nails down the rate. Integration lets you essentially add up all those tiny instantaneous rates over whatever time period or area you care about. It's the mathematical machinery you need to calculate the total volume, the cumulative effect.
Ah, okay. So it's like, the speed, the water's flowing, the rate, and integration helps you figure out the total amount that went by.
Exactly that. The sources really hammer this home. For a proper quantitative grip on cumulative runoff, you need calculus. The models people use to predict runoff, they often involve integrating rates, rainfall rates, infiltration rates, stream flow rates.
Okay, got it.
It lets you quantify the input, which is the rain, understand the processes happening in the middle, like infiltration, and then calculate the output, the total runoff.
That makes it feel much more tangible. You're not just watching water, you're using these math tools to build models, analyze things, predict what the whole system might do.
And that leads to really vital applications, say, in forest management. If you understand the link between how hard it's raining, that's a rate, and the total runoff volume you can predict by integrating, well, then you can assess flood risks much better, or predict water availability downstream, or even design drainage systems more effectively. It's practical stuff.
Okay, so let's try and summarize this then. The big takeaway from the sources is differentiation helps us describe the rate water moves, driven by all those hydrological processes,
The instantaneous part.
while integration is the essential math tool we need to calculate the cumulative water runoff in that forest watershed.
Exactly. And for you as a student, seeing this connection, well, it shows these calculus concepts aren't just theory. They're fundamental for understanding and quantifying the natural world. It makes them feel, hopefully, a bit more relevant, more approachable.
Absolutely. So here's a final thought to chew on. We talked about measuring the rate of river flow,
Right.
using that idea of differentiation to understand rates at different spots, maybe over time. How could integration then help you predict the total volume of water, say, during the entire spring snowmelt or after a huge storm? Think about how that prediction could be critical for managing potential floods.